Hello and welcome to all students. This is a BSc first year class, and today we are going to see about properties of some continuous functions. And in this lecture we state one theorem, and let us write the proof of that theorem. So statement of the theorem is based on the continuous function, and let us state the theorem. If a function f is continuous at x is equal to c, where f of c is not equal to 0. See once again, if a function f is continuous at x is equal to c, where f of c is not equal to 0, then positive number delta can be found such that f of x has the same sign as f of c. Once again, if a function f is continuous at x is equal to c, where f of c is not equal to 0, then the positive number delta can be found such that f of x has the same sign as f of c. For every value of x in the interval c minus delta, c plus delta. Let us write the proof of this theorem. Given f is continuous at x is equal to c, therefore limit of f of x tends to c is equal to f of c. So this is the definition of continuous function. That is, for given epsilon greater than 0, there exists a delta greater than 0 such that whenever mod of x minus c is greater than 0 and less than delta, this must implies mod of f of x minus f of c is less than epsilon. That is x minus c is greater than minus delta less than delta, and this must imply that f of x minus f of c is greater than minus epsilon less than epsilon. That is, x is greater than c minus delta less than c plus delta, and this must implies f of x is greater than f of c minus epsilon and less than f of c plus epsilon. Now let us take case 1. In the first case, suppose f of c is greater than 0. Take epsilon greater than 0 such that epsilon is less than f of c. This implies that f of c minus epsilon is greater than 0, and this implies that f of x is greater than f of x is greater than 0. And this implies f of x is positive. Case second, suppose f of c is less than 0. So in first case, whenever f of c is positive, f of x is also positive. Now in case second, suppose f of c is negative, then what will happen? Minus f of c will be positive, and take epsilon greater than 0, but epsilon is less than minus f of c. This implies that f of c plus epsilon is less than 0, but f of c minus epsilon is less than f of x less than f of c plus epsilon. And this implies that f of x is negative. Okay, so whenever f of c is negative, f of x is also negative. So thus we proved that if f of c is not equal to 0, then there exists some neighborhood of c in which the values of f of c has same values, f of x has same values as that of f of c. Let us go to the next theorem. If f of x is continuous in closed interval a comma b, then f of x assume every value between f of a and f of b. Once again, if f of x is continuous in closed interval a b, then f of x assumes every value between f of a and f of b at least once in closed interval a comma b. Once again, if f of x is continuous in closed interval a b, then f of x assumes every value between f of a and f of b at least once in closed interval a comma b. Let us write the proof. Given that f of x is continuous in closed interval a comma b, let d be the number in between f of a and f of b, and d lies between f of a and f of b like this. Construct a function f of x equal to f of x minus d in closed interval a comma b. F of x and f of d both are continuous functions on closed interval a b. Therefore, f of x is continuous. Therefore, f of x is also continuous function on closed interval a b. Now, f of a is equal to f of a minus d, which is less than 0, and f of b is equal to f of b minus d, which is greater than 0. Assume that is f of a is less than 0 and f of b is greater than 0. Also, f is continuous in closed interval a comma b. So, by property of continuous function, f of x must vanish in closed interval a comma b at least once. Therefore, there exists a number c in open interval a comma b such that f of c is equal to 0, and this implies that f of c minus d is equal to 0. This implies f of c is equal to d. Okay, so that is, therefore there exists c in open interval a comma b such that f of c is equal to 0, and this implies that f of c minus d is equal to 0, that is f of c is equal to d. But d was a arbitrary number between f of a and f of b, and there exists a c in open interval a comma b such that f of c is equal to d. Therefore, f of x assumes every value between f of a and f of b at least once in closed interval a comma b. Let us go to the next theorem. If f is continuous in the closed interval a comma b, then f of x attains its exact upper bound and exact lower bound at least once in closed interval a comma b. Proof: let m is equal to least upper bound of f of x in closed interval a b. Assume that f of x is not equal to m for all x belongs to closed interval a comma b. Therefore, m minus f of x will be not equal to 0 for all x belongs to closed interval a comma b. Let us construct a function capital F of x is equal to 1 upon m minus f of x for all x belongs to closed interval a comma b. Function f of x will be continuous and hence it is bounded in closed interval a comma b. function f of x is continuous and hence it is bounded in closed interval a comma b. Therefore there exists a list L list upper bound and u L and u such that therefore there exist two numbers L and u, म्हणजे lower bound and upper bound for the function f of x, capital F of x. Therefore capital F of x is greater or equal L, less equal u for all x belongs to closed interval a comma b. That is that is 1 upon m minus f of x is greater or equal L, less equal u for all x belongs to closed interval a comma b. This implies that m minus f of x is greater or equal 1 upon u, and this implies that m minus 1 upon u is greater or equal f of x. That is f of x is less than or equal to m minus 1 upon u for all x belongs to closed interval a comma b. Contradiction to m is a least upper bound of f of x. Contradiction to m is a least upper bound of function f of x. Therefore f of x is equal to m for at least one x belongs to closed interval a comma b. Thus f of x attains its exact upper bound at least once in closed interval a comma b. Similarly, we can show that f of x attains its exact lower bound at least once in closed interval a comma b. So this is the end of this proof. So let us go to the next, sequential continuity. Let us define what is meant by sequential continuity of a function. Let function f of x is defined for every x in some neighborhood of C. F is said to be continuous at x is equal to C. F is said to be continuous at x is equal to C if there exists a sequence Cn such that whenever Cn converges to C, this implies that f of Cn converges to f of C. So sequential continuity. Let function f of x is defined for every x in some neighborhood of C. In some neighborhood of C, f is said to be continuous at x is equal to C if there exists a sequence Cn such that whenever Cn converges to C, f of Cn must converges to f of C. In this case, we say that function f is continuous at point x is equal to C. Or we define like this: limit of f of x extends to C is equal to f of C if and only if whenever limit of Cn as n tends to infinity is equal to C, this must implies limit of f of Cn as n tends to infinity is equal to f of C. So this is the definition of sequential continuity of a function. Now the following URL gives graph of all type of functions very nicely. You can take a screenshot of this URL, type in Google, and just you enter a function. In the box you will have a graph of that function. Okay, very nicely. So take a screenshot or write down this URL in your notebook and go to the Google and find out the graph of functions. Okay, and this is the end of this lecture. Thank you for paying attention. Thank you very much.